Welcome back. This video is going to give you an overview of some special random variables that come up in a lot of situations and will be very useful to us. So in the last video, I defined what a random variable was, and then we went through a very simple example to illustrate and just give you an overview of the types of things we typically do with a random variable. And so that was summarized in this box. Now we're going to see how all of these fundamental characteristics work for specific random variables. This video has been a very difficult one for me to make because it's two full chapters in your textbook, and if we were going to really do justice to this topic, we would devote at least 2 weeks to those two chapters. To really do justice to them, we would want to spend probably 3 or 4 weeks doing this. The thing is, this is not a course in probability and statistics, it's just a course in statistics. And so we assume that you've already had the probability part of this, but I find these special random variables to be kind of difficult. I didn't understand them the first time through as well as I should have, and that's why we spend time reviewing them in the statistics course. So then the question I've been struggling with is, what do you need to know about these special random variables in order to do statistics? And that's kind of my filter for what I'm going to cover this week, is what do you really need? And so we're going to be doing estimation, and then we're going to be talking about confidence intervals, hypothesis tests, and I want you to have the basic skills with these random variables in order to do those topics in statistics. All right, so what are these these basic things that you need to know about different special random variables? Well, I think my table here does a pretty good job of summarizing the definitions of these properties. To find them for specific random variables, I think the best place to go is Wikipedia. Now, your textbook's also a very good place to go, but Wikipedia does a great job of summarizing them in a very consistent way. So let's just go to the most famous of distributions, the normal distribution. And what you'll see is, off to the right, we have a table that gives you a list of these fundamental properties. So what are these fundamental properties? Well, the first thing that you need to know about any random variable is, what are the parameters? And so the parameters are clearly identified here. So with a normal distribution, we have two parameters, the mean and the variance. By the way, they give you some pictures up here with various values of those parameters. But let's just go over to my document camera for a second, and I'm going to sketch one out for us. So if we had a normal distribution, this is one of our special random variables. This is the PDF. So this would be the PDF, and this PDF is a function of two parameters. So the first is the mean, and then the second is going to be the dispersion. I always like to write my my variances of normal curves up here. And so this is the PDF of a normal curve. All right. So the first question is, what are those parameters? It's identified right here. If we go to another very famous distribution, the binomial distribution, the page is organized in the same way. So what are the parameters of a binomial? Well, remember, a binomial is where I like to think of it as I flip a coin n times, each with probability p of getting a head, and I count the number of heads. So the parameters of a binomial are just the number of coin flips, or number of trials, is the generic term for a coin flip, and the probability of success, or the probability of a head, p. So we have our parameters clearly identified. Another distribution that you should have seen back in basic stats is the exponential distribution. So again, what are the parameters? Well, there is one parameter, which is lambda, which is the rate or inverse scale parameter for this. Okay, that's the first thing that we need to know about any random variable is what are the parameters. The second thing we need to know is what is the PDF. So if we go back to a normal curve, the PDF is given to us right here. Now this PDF is typically an equation that is that involves the parameters. These parameters control the shape and the location of the distribution. So in this case, the mu moves the normal distribution, moves the center of the normal distribution around. Sigma determines how dispersed it is. It's also usually a function of certain constants like 2 pi or the square root of 2 pi, negative 1/2 up here. And then finally, you're going to see an x in there, which is the input to that function. So it doesn't matter which random variable we have, they are always a function of the parameter, some constants, and the variable itself. Let's go look at the binomial. Here is the PMF for a binomial. All right. One more thing about PDFs. Let's just go over to my my document camera again. So this is my PDF. I also want you to know how to find these PDFs in R. Okay, so we can think about f at x has a certain equation. So in this case, it was 1 over sigma squared times the square root of 2 pi e to the negative 1/2 x minus mu over sigma squared. But you don't need to remember that if you're using R. So in R, there is a series of functions for all the special random variables that we typically encounter. So the special function, I'm going to use red for R, is the D series of functions. So D norm gives us the distribution or the PDF for a normal curve. So you pass to this some number of, some x, so I give it some x, and then I can also give it the parameters. So the parameters are mu, R parameterizes it with a sigma rather than sigma squared. That's fine. And this will give me the equation of a normal curve. Now, what you should note is that there is a D function for all of them. So if I do D binom, I will get a binomial probability. So I would give it some x, and remember the parameters are n and p for a binomial. Or for an exponential, it is d exp. Again, I give it some x, and I give it my lambda value. There are others, d gamma gives me a gamma function with the parameters alpha and beta. All right, so let me kind of go illustrate how why this is interesting in R. So I'm going to make myself a sequence of some x values. So let's say x is a sequence from -4 to +4, and we're going to have it a step size of 0.1. So this is my x. Now if I do D norm, this is going to be the distribution. It gives me the PDF of a normal. So I'm going to go plot this. So let's go plot x with D binom of x, and then I'm going to say type equals L. That just connects the dots. Now there are some additional optional arguments here. I could specify the mean, I could specify the variance. If I don't, I get something with a mean of 0 and a variance of 1. Oops. I meant norm, not binom. And so what do you get when you plot this? You get the PDFs. All right, so make sure you know how to use these probability functions in R. Let's just go get some help on this. So what you're going to see is we just found the density, the probability density function for that. All right, back to my course packet. Let's go with the course packet. What's the next thing we need to know? Well, the next thing we need to know is the CDF. So remember, the CDF just gives us the area under the curve up to some value. So the question that we need to address is what do we need to do with the CDF in statistics? So what we typically need to do with that is to find tail probabilities or slice probabilities. So I'm going to just give you a very quick summary of the types of stuff we typically do. So, we might have some x1 value right here. So that's a particular x. And I may want to know what is the area in that tail. Okay, so in notation, this would be what is the probability that my random variable x is, say, less than or equal to my little x1. Well, the answer to that is just the CDF, so we usually denote the CDF by a big F, not a little f, evaluated at x1. Now, in R, the way we do this is we use the P functions. So P norm will give us the CDFs. So if I say P norm of x1, I got to give it a mu and a sigma, that finds that probability. So as an example, let's just go over to R for a second. If I said something like P norm, got to spell it right, minus 1.96. So this is, and I'm gonna give a mean of 0 and a standard deviation of 1. So if you want, you can give those parameters, but as you can see off to the right, those are the defaults. So they're not really necessary. I'm just going to get rid of them. So this is going to give me that tail probability. It's a very famous tail probability. The answer should be 2.5%. And so sure enough, it's about 2.5%. And so that would just say that the area to the left of minus 1.96 is 2.5%. All right, back to the document camera. The other type of question that we may have with a normal curve is what I refer to as the greater than question. So I'm going to do that in black. And so let's say I have another value here, x2. And so what is the probability we're off in that black tail? So we'll do this in black. What's the probability that x is greater than or equal to x2? Well, the way we do this with our CDFs is we just take 1 minus the probability that we're less than or equal to x2. We can be a little sloppy with our equal signs with the continuous distribution. So 1 minus f at x2. So if we translate this into R, this would be 1 minus P norm x2 with the mu and sigma handed off to it. So as an example, I'll pick another number. Let's say that x2 is the value 1.645. That's a very famous number in statistics because that's going to give us 5% here and 95% to the left of that value. So let's just go try that in R and just confirm that it works. So I'm going to take 1 minus P norm, 1.645, and you got to spell things right, otherwise it doesn't work. You're going to see the area in the tail is about 5%, just P norm 1.645 should be about 95%, and sure enough it is. All right, that's another thing that we often want to do. Now, the next thing that we often want to do is to invert the PDF of some distribution. So the question that we may have is, I could ask this question. For what value of x do I have gives, I'll just say that, the probability that this random variable x less than or equal to x is equal to, say, 95%. All right, so what is this value of x? Now, notice what I'm doing. I'm giving you the probability here. Actually, I'm giving you this probability. I want 95% of the area to be left to the left of some value, because I'm just inverting the CDF. Well, the answer in R is to use the Q functions. So Q, 0.95, got to write it here, with a mu and a sigma will give me that x value. So the P functions give you an x and return the probability. The Q functions give, you give the probability and you get the x. So this should be 1.645. Let's go just make sure that works. So if I do Q norm 0.95, this should be 1.645. So we've just undid what we did with the CDF. What I want you to remember about this is that we have these P and Q functions for every special distribution. So we can do P exp gives us the one for the exponential distribution. P binom does it for the binomial. Likewise, Q for these. So Q exp, Q binom works for the exponential and the binomial distributions. All right. If we go back to Wikipedia, what you'll see is that sometimes there are simple closed form expressions for these. In the case of the exponential distribution, we have a simple closed form expression for the PDF, CDF, and the quantile function. They don't always exist. So the normal curve has no simple closed form expression for the CDF. You have to evaluate that numerically, which is what R does. Likewise with the quantile function, you don't have one for the normal. Let's just go see what it gives us for the normal. And yeah, this is an internal function that we have to use to evaluate this. All right. The last thing that we need to know about these special random variables is what is their mean and variance. So in the case of a normal distribution, the answer is very easy. The mean and the variance are the two parameters, mu and sigma squared. In the case of other distributions, the answer is not so simple. Okay, so there's the mean and the variance are, we would like to be able to express these as functions of the parameters. So one of the your turns is to show that the mean of an exponential is just 1 over lambda, the parameter. The variance just 1 over sigma squared, the parameter. Likewise, for a binomial, we can express the mean and the variance as a function of the parameter. So the mean is just n times p, the probability of a head. Variance just n times p times q, which is 1 minus p. So we want to be able to express that. Again, if this were a full-blown course on probability theory, we would spend a couple weeks walking through the different mathematical techniques that are used to compute those means. So sometimes they're easy, as in the case of a binomial. Sometimes they take a lot more effort. In the case of gamma distribution or beta distribution, we would have to study certain mathematical techniques and tricks. Hopefully you've seen those in your probability class. If you haven't, it's good for you to know those techniques. But for now, in a stats course, we're just going to go to Wikipedia and look up what is the mean and the variance as a function of the parameters. All right, I want to cover just one more function in R. So we've got to go back to R. And so with any special random variable, there are 4 functions. So D, P, Q, and R. If let's just go look at the binomial page, and you're going to see the same 4 functions: D, P, D, and R. So this is the probability mass function, the CDF, the inverse CDF. What is this R function? So the R functions for a special random variable generate random values from that distribution. So I'm going to set my seed. This, if you set the seed, you will get exactly the same random numbers as me. So I'm going to set it to my favorite seed, which is 1, 2, 3, 4, 5. So you should go set your seed. Now let's go type R. I'm going to do normal random variables for now. So R norm. And the first argument is how many random variables do you want to generate? So let's just generate 1 for now. And you'll note that we have optional arguments, the mean and the standard deviation. So we have just generated a random number from a normal distribution. If I did R5, I will get 5 random numbers from a normal distribution. So let's now generate many random variable values. Maybe I'll do 1,000. And I'm going to save those 1,000 values in a vector called x. So if we do a length on x, it should be 1,000. If we do a head, you'll get to see the first 5 values, or 6 values. Now, just to convince ourselves that this is a normal random variable, let's go make a histogram. So if I do hist on x, we'll get something that looks pretty normal. And sure enough, that's about what we have. Another thing that we could do is to plot the density of x. At this point, what you should do is go work problems from Devore. So this slide gives you all the formulas that are on Wikipedia for the binomial distribution. And you could just jump into problems, since this the binomial distribution gets covered thoroughly in any probability class. And so if you remember the binomial distribution, just go start working problems, and that's probably good enough. If you're struggling, I have various videos that you can watch. So I have some videos that I have made when I've taught probability theory, and you can watch my explanation of the binomial distribution. Hopefully you don't need that, but if you do, go watch it. And if you get stuck on these problems, watch my videos. But I would start by trying the problems. Then moving on, we have the normal distribution. I summarize the key properties here, and you have various problems. Again, if you're stuck, go watch my video. Hopefully you don't need to do that. Then we have another slide on the exponential distribution. Again, if you get stuck, go watch my video. So just make sure that you're able to do these basic tasks with the special random variables that I've identified.